You know, I can't answer what time period to use, but that's a choice in your analysis that you want to specify. Here's actually kind of an example of that. I think I showed this in the first year, but I don't really remember. I'm sure you guys don't either. Paul Adler, who's worked a lot with Bill Parton, Steve DeGrasso, they wrote a paper back in 2007 where they did a life cycle using the day-set model, the same thing you guys will be doing. And they, you know, this was for sort of an imaginary biofuel production system. And they looked at a bunch of different systems. You can kind of see them over here. You know, switchgrass, reed canary grass. They looked at conventional ag systems where you could use the corn for ethanol, you know, corn stover for cellulosic ethanol. You could use the oil from the soybean for biodiesel. So they looked at sort of a maximum use of this stuff, and then they looked at hybrid poplar. They actually looked at fuel conversion life cycles as well as kind of bioenergy. So they looked at if you took this stuff and you used it to make electricity, you know, what does it look like from the standpoint of you know, the greenhouse gas emissions associated with the biofuel production and the displaced. Well, actually over here, this is for each of these systems. They said, okay, what is the value of the biofuel in terms of its displacement of fossil fuel, right? Which is primarily going to be, you know, how much biomass can you grow in this particular location, and how much fuel can you make out of that amount of biomass. So that's a computation you can do, and you will be doing in your analysis. And so you can contrast different, you know, feedstock systems. And so, you know, basically switchgrass and poplar could produce the highest amount of fuels on a given land area that would displace fossil fuels. So that's part of the greenhouse gas balance. The other one, though, of course, is what are the greenhouse gas emissions associated with the production? And there's lots of different components to that. And then they basically took the two and said, okay, what's the net? So if you take the displaced, you take the fuel that is capable of displacing fossil fuel, and you subtract from that the greenhouse gases that went into the feedstock production. What are you left with? And these are in terms of percent reductions in net greenhouse gases for these different systems vis-a-vis the, you know, the fossil, the fossil fuel equivalent. So they in their system they said, okay, if you use corn, soybean, and you extract the ethanol, you extract the biodiesel, you do the full life cycle analysis. You know, they came up with the estimate that actually you could get a 50% reduction in greenhouse gases net relative to fossil fuels.
I was just wondering, if we're doing poplar, why is the difference in your show?
So I'm getting to that, yeah. Okay, getting there. How do you get a negative? Well, that would be if the, basically if you essentially had nil or almost nil greenhouse gases associated with the production of the biofuel feedstock, but you also had, and so you've got displacement, and then you produce additional greenhouse gas offsets. Okay, one of which could be if a byproduct, for example, in cellulosic, you produce lignin, and the lignin can produce extra electricity. You know, that can help push this negative. But the big thing is going on here is in both the switchgrass and in the poplar, they're getting a buildup of carbon in the soil. So soil carbon sequestration. So if you factor that in, you're saying you're producing biofuels, displacing fossil fuels, but you're also taking CO2 out of the atmosphere net and putting it in the soil. That's how you get the negative.
Is that just because they're bigger?
That's because they allocate enough enough carbon below ground. We're going to go through that here in a second to essentially build up the carbon stocks in the soil. Whereas under, say, a corn soybean rotation, they might just, at best not change. But we'll get to that in a second. The reason for the near term versus the long term is that actually this soil carbon is kind of a transient phenomenon, right? Okay, you can build up soil carbon for maybe 10 years, and after that you reach a new equilibrium. And so if you take this out longer, then essentially that soil carbon contribution to the net greenhouse gas life cycle is a lot smaller. So that's why the difference between the long term and the short term. So another kind of way of looking at this is actually from the same paper, but John broke out the emission, kind of the feedstock production footprint in a slightly different way, which I think is useful for you guys as you're thinking about how are you going to compile all the data to do this greenhouse gas footprint. And essentially you can say, okay, for feedstock production, I've got something, I've got emission sources that can be associated, you can be classified as kind of industrial emissions. So what are those things? That's like the energy, the fossil energy you use on the farm for the production, the transport of the biofuel feedstock to the plant, and the emissions associated with the biorefining component of it. Okay, so that's kind of the industrial, includes the feedstock as well as the conversion. And then you've got biogenic emissions, okay? And on the positive side of things, on the net emissions, so greenhouse gas emissions, the bad part, you primarily have, nitrous oxide emissions, okay? Either directly, I'll get into the direct and indirect in a little while. Or in this case, you might have, an uptake of soil carbon, which counts as a net emission, or an uptake, a buildup of soil carbon, which is a net uptake of CO2. And then you've got sort of the displaced emissions from the actual production of the biofuel. So this is another way to look at the different components of emissions associated with that feedstock production in the biorefinery. So, you might kind of have that in mind as you're going through and saying, okay, what do I need to account for in my analysis? What are the different pieces? Okay, how many people here know what solar organic matter is? I know at least a few. Who kind of does? Okay, so we're going to speak a little bit to the guys that don't, and that's all right, because I don't know, thermodynamics of turbine engines and stuff like this either. So, okay, so when we're looking at the feedstock production, we're talking about greenhouse gases. We're primarily talking about two things: carbon dioxide and nitrous oxide. Okay, so let's talk about the carbon first a little bit. Just a few kind of basic facts. Why do we care about it? Why is it important? One thing is that soils actually contain more carbon in organic form than vegetation and all the CO2 in the atmosphere combined. So it's the biggest part of the terrestrial carbon balance, if you will. It's about probably 3 times the amount that's in vegetation, which most people wouldn't intuitively think. And typically you have in most mineral soils, okay, mineral soil is where you have sand, silt, and clay, and you've got some nice organic matter in it. An organic soil is not the soils they use to grow foods for Whole Foods. It's a different organic. Organic soil is like a peat soil. Okay, it's mainly organic matter, not very much mineral. Talk about it. You guys will be, nobody decided to do Florida, so probably no one's going to have organic soils in our analysis. If you're going to do Florida in the energy kingdom, you're probably going to have organic soils.
So in that analysis, is the goal, are we going to be assigning, or is it going to be our choice whether or not to assign some sort of price to like the net carbon that we're pulling out, or is it just, you see what I'm saying, like, so we have 2 competing technologies that, for the sake of argument, are equal in all other ways, right? we have one that's depositing more carbon back into the cycle, and one that's maybe removing some. So I mean, I think we would want to choose one and put any back in, but what if our processes aren't in price?
That's something you could do. You could, if you want to enter that into your analysis, you might say, okay, pretend there's well, actually, you could do it now. You could say, gee, I'm going to go to the voluntary carbon standard, and I know right now they're paying, $12 a ton for carbon dioxide offsets. So I'm going to make that part of it. Or I think from that standpoint, you could also say, we anticipate that the Waxman-Markey legislation for a cap and trade system in the U.S. is going to be revitalized next year. So in our business plan, we are, factoring in a likely $40 a ton CO2 offset, and we believe that, our systems are going to be shown to satisfy, these requirements, and therefore, if you calculate the amount of carbon storage you might get in your system relative to the baseline, the original what's there before you start your project, you could, that would be encouraging to say add that into your, into your system, or do an analysis, if, with and without is easy enough to do. But okay, so that's a great question. Just again to give you sort of, a hands feel, because you're going to be running models and you're going to get numbers out, and do they make any sense? Typically somewhere on the order of about 40 to 20 tons of carbon to be in the top, meter of soil. When you're working with a century model or the DayCent model, you're actually going to be really looking at the changes just in the top 27 years. But I think that's probably where the biggest changes are going to occur. Tons per hectare, or megagrams per hectare. Okay, everybody's familiar with that. When you run century or DayCent, you're going to get units in grams per meter squared. Okay, and then you can just 1,000 grams per meter squared is the same as 10 tons per hectare, 10 megagrams or 10 metric tons. And, and of course, 1,000 grams per meter squared is the same as, yeah, so that's, or 10,000 kilograms per hectare. Anyway, so that gives you just kind of an idea of the sizes that you're looking at. In terms of the contribution of this soil carbon to the, to the greenhouse gas, loading in the atmosphere and things like this, if you're looking at systems that don't have a big standing vegetation component like trees, okay, the main carbon in the ecosystem is in the soil, and if the soil carbon stocks are declining over time, then you're getting a net efflux of carbon dioxide to the atmosphere. And if they're increasing over time, you're essentially getting a net flux from the atmosphere. Now, talking about soil organic matter is different. Okay, that's the carbon, oxygen, hydrogen, nitrogen in decaying vegetation and things like that. But just as a general rule of thumb, you can, use that standard conversion of about 58% of soil organic matter is made up of carbon. Yeah. So soil organic matter is